So now we are going to look at the equation for Fleming's left hand rule. So suppose we have a magnet like this. And a coil, a wire, okay, going like this. And inside the wire, there has to be some current that's going like this. The length of the wire is also given. The length within the whole thing, okay? The length is 4 meters, the wire. The magnetic field strength is 1.5 Tesla. And that's basically when the magnetic field itself, when we make the magnetic field, you guys need to remember this magnetic field is 90 degrees to the conductor, okay? So I'm just going to write it so that you guys do not forget, provided that the conductor is perpendicular to the field, the force experienced by it is given by F equals to B I N L. Now let me tell you what exactly this equation is. So you can remember as force equals to Bill, and this is basically the force experienced by conductor, and this is the magnetic field strength, this is the current, and this is basically the length of wire exposed. So that means the length of wire that is within the magnetic field. Is it clear, everybody? Now, so what you're going to do is simply use the equation. In this case, we're going to say, okay, F is equal to Bill. B is actually equal to 1.5. The current is 2 ampere. I didn't give it to you. And the length is 4. So the total force that this conductor is going to experience is 12 newtons. And then you can find the direction through the left-hand Fleming rule, which is basically your index finger towards the south. The current is going into the page, which means the force is going to act downwards. You can check as well. Is it clear, everybody? Let me know if you have a question. Now, the question is then that's pretty simple. So what if the conductor is placed at a different angle? Okay, so if you're looking at from the top view and you see a magnet, and you see the wire is like this at a certain angle, okay? The current is the same going. Now the field really in this part, if you make the field is at a certain degree theta from this. Now the field must be perpendicular to it. It must be perpendicular, okay? So we have to make sure that it's perpendicular to the wire. So the perpendicular would be actually the component that goes this way, and the parallel component to the field is this one. So this component is basically the sine theta one. So what are we going to do is that in this case then we're going to say that force is equal to BIL times, because we want, you know, current to be perpendicular, we're going to multiply sine theta. Is it clear, everybody? Now, interesting fact is that if so, we would say on the parallel side, there will be no force, and the reason is because the angle will be 0 then, and if it's completely parallel, sine 0 is 0, so the whole equation becomes 0. But at 90 degrees, when the theta is 90 degree, then sine 90 is 1, which is basically gives us the maximum force. Is it clear, everybody? Any questions? Let me know. Okay. Now, at any time, they ask you exactly what is magnetic flux density, okay? So you just need to explain the formula, and I'm just going to write it so that you guys know exactly how to explain the formula. So definition of magnetic flux density, which is B that we're talking about right now. So this definition would be the force acting per unit current per unit length of a wire placed perpendicular to the direction of magnetic field. Now, how do I know this? Because like we said, F is equal to B, I and L, and I want to define B, so I will make B the subject. Then F will be divided by I and L if it's perpendicular. So that's why I've written, if you look at the definition, the force acting per unit means divided by current, per unit length divided by length of the wire placed perpendicular direction of field. Is it clear, everybody? So what you're going to do is you just need to explain the whole formula. Any questions now? Please let me know. Okay, Suman, Aman, Hassan and Gatika. Everything is clear? Crystal?
Yes, sir.
Okay, that's pretty good. It's pretty good. Okay. So now, we would be basically doing an experiment. Please write. Experiment which is called current balance experiment. That's the name. Now I want you to basically, the way I have drawn the drawing here, okay, I just copied it from my old notes. So this is the type of drawing that is expected from you in paper 5 as well. So reasonable drawing with reasonable labeling. Okay, so please draw this. First of all,
ساجر ويطلع أكيد هو الجو.
इसमें the thing is, the only thing you should understand is कि बेशक it is not 3D, it's fine, but like I have written rigid wire, I've clamped it to show the wire is clamped, I've not left it open, and then I have put variable resistor, ammeter, battery, the things I need. So that's very important. Understood? Ideally, you should be spending like 5 minutes at least on the drawing so that everything is there and there's no room for any mistakes there. Okay, now, so this apparatus measures the magnetic force on a current carrying conductor placed perpendicular in a magnetic field. So first of all, in the first point, I'm going to say a magnet is placed on a top pan balance. All right. Then part 2. Initially, the switch is open, as you can see from the drawing as well, and reading on the balance is set to 0. So why do we want to do this? Because when the switch is open, the balance is going to show you the weight of the magnet that is placed on top of it. So if you set it to 0, it means now the balance won't read anything. It will ignore the weight totally, and now we're going to look at exactly what's going to happen to the force that will act on the wire or the magnet when the switch is closed. Okay, now part 3, I'm going to write it here. Okay, switch is closed, and so the current flows in the wire. Number 4, due to this, and according to Fleming's left hand rule, the wire experiences a force in upward direction. Since, okay, before we write this, I just want to show you how. So when the switch is closed, you see this is the positive terminal, this is the negative, so the current will go from here to here, and now you can use the Fleming's left hand rule. So your index finger should be towards the south, the middle finger should be in the direction of current, that's towards the right. So you'll see that on the wire the force is on top, like this. Now that's what I've written up till now. Okay, number 5.
So where does the second finger point?
That's going to be towards the right. in the direction of current?
Isn't that the index finger?
Oh, isn't index finger the first finger?
Yes.
So second should be towards the right, index should be towards the south.
Got it.
Now, check this out. So, since the wire is rigid, and that's why I've written rigid wire cannot bend or twist. So, do remember that. Rigid, according to Newton's third law, equal and opposite force is applied onto the magnet on the balance. So this would mean the balance will now show the value of the force on it that is basically experienced by the wire and the magnet, because according to Newton's third law, the action and reaction forces are same in magnitude. Do you guys understand this? So then this will give the value of the electromagnetic force. Now, if you want to read more about this, okay, and you like, okay, I want to, study about it. So that's my suggestion. I learned this the hard way so that you don't. But if you want to really go deep into it, you go and search George and Griffin experiment. Okay. Any questions, please let me know. I hope everything is clear. Aman, you understand? Hassan, Suman, and Gatika?
Yes, sir. In the fifth step again.
Okay. You see, we do realize, Gatika, that according to Fleming's left-hand rule, the force on the wire is F. You understand?
Yes, sir.
Then Newton has said that if body A does an action on body B, what is happening? The magnet in this is applying a force on the wire, right?
Right.
So an equal and opposite reaction will be experienced by body B by A, which means an equal and opposite force will act on the magnet by the wire. You agree? Which means the magnet will be pushed downwards equally with the same force, and that force will be shown on the pan balance. Do you understand this? And that is the
Yes,
force
sir.
we want, right? Now, in paper 5 perspective, what you're going to do is you're just going to write, okay, I'm going to change the current, I'm going to, find different forces, and for that, I'm going to conclude blah, blah, blah. So the point is that this is the reason why variable resistor is there. So to control the current. That's for paper 5. For paper 4, writing point 4 and 5 is very, very important. Do you understand? Because that explains how this whole thing works. Understood?
So we basically need to know how all of the steps.
Of course you know. Of course you need to. It's gonna help you in both the papers, right? Alright. Should I move forward then? What do you guys say? Now, so the next thing is magnetic effects on moving charges. Now check this out, please. So imagine there's an infinite magnetic field that is acting into the page like this. Just imagine this. Like I said, across means into the page, so it means that this is the field of infinite nature. Okay, now let's assume that a positive charge, it could be really anything, a positive charge, maybe an alpha particle. Alpha particle is just a helium nucleus with +2 charge on it, enters perpendicular to the field. So it's perpendicular to the field, enters here. Is it clear, everybody? With the velocity v. So when it enters, you guys need to understand that according to Fleming's left hand rule, your index finger should be pointing towards the page itself, because the field is going into, so index finger is pointing towards the screen right now that you're looking at, and your middle finger should be actually pointing towards the velocity, the direction of the current or the velocity, right? So it's moving like this. So you might realize that basically it will feel a force upwards. Please check if that's correct. Please do this. Let me know if you can, because this is important. So, what does force do? It basically turns this, like this, okay? So when it has reached this point, now the velocity direction is this way. So let me just make, at this point, let me make velocity with the, so velocity right now is in this direction. Do you guys agree? Now, use the Fleming's left hand rule again. So your index finger towards the screen that you're looking at right now, the middle finger will be going towards up because the velocity is up, and you'd realize that the force is basically acting towards this point. Do you guys agree?
Yes, sir.
That would mean that this would now turn, oh my god, this would now turn this way. Okay, now when it reaches here, so the velocity is like this, which means velocity is exactly to the left. And now you use the Fleming's left hand rule again, index finger towards the screen because that's what you're looking at, and then you turn your wrist in such a way that your middle finger should be towards the left, which means that you realize that the force now is acting downwards. You see? Now check this out. This force will then cause it to turn this way. When it reaches here, now the velocity is in this direction, which means if I make the velocity vector, it's going to be like that. So now index finger towards the screen, towards the field, middle finger downwards, and now your thumb points to the right, which means that this is going to go this way. The force is this way. And now when it turns like this, because of the force, it goes right here. Now the velocity is here, which means that the velocity vector is towards the right. And now if you apply the Fleming's left hand rule, see index finger towards the field, the middle towards the right, then the force is going to be upwards. So this, if this is an infinite field, then it's gonna keep on moving in a circle. Do you guys understand this? Interesting, right? In 10 minutes, please rejoin. Now, so what we can do is we can write this down. We can say a helium nucleus enters a large infinite uniform magnetic field and moves upwards due to experiencing a force, right? And how do I know this force is being experienced? Because of, according to Fleming's left hand rule. Got it? So the idea behind this is that, now this is something really important. Let's check it out. Whenever, it's not just about this one, whenever an isolated means that there are no other forces really, charge enters a magnetic field perpendicular to it, it will experience a magnetic force according to Fleming's left hand rule. Now, the second point is that the magnetic force alters the direction of velocity vector and therefore alters the direction of instantaneous current. Instantaneous current means wherever the charge is moving causes, current. Causing Fleming's left hand rule to continuously act, okay, towards, okay, continuously acts. Now here I would say that the force continuously acts towards the center of the curved path. Okay, if you look at the whole thing, do you remember something about this? Something that moves something in a circle?
Centripetal force.
Centripetal force. That is 100% correct. Which means, before we go into that, Let's first derive the equation for a solitary charge moving, right? So let's do this small derivation, and then we'll conclude the whole thing after we've driven this. We drive that. Okay, for the derivation for force on an isolated moving charge. Now we know that when we drew this, you guys realized that the magnetic field was into the page like this, which is perpendicular, right? At any point where the velocity was basically in a single direction, the force was acting perpendicular to that, right? Like this. That basically brings us to F equals to B, I, and L, because there is an instantaneous current. Now, B is B. Current is basically determined by the charge that is moving per unit time, and there's length. If you notice, length over time is what? Can you please tell me that?
Velocity.
Velocity, which means then the force will be equal to B times Q times V, and that's the formula we're looking for. So that's the small derivation, BQV, and that's the other formula for the single charge. So BIL is for the whole current moving in a single wire, and then BQV is basically for a single isolated charge. So this is the force, okay, magnetic force. This is basically magnetic field strength, and this is the charge, and charge of moving particle. This is important because it should be moving, otherwise it would not feel any force. And V is the velocity of particle, whatever that particle is. Now, so what we got to learn, that is, what we have learned from all of this is that the force that we've just seen, that this force can be regarded as the centripetal force. And if we do that, then can I say, in this particular section, can I say that the force of magnetic force is equal to the centripetal force, and then magnetic force is given by BQV and centripetal force is given by half, I started writing mv square over r, right? Is it clear, everybody? Now, so if I make r the subject of this equation, this will be mv square over bqv. V and V will cancel out, so which means that R will be equal to mv over bq, and that's the best friend equation that you're gonna have. Okay, remember this equation, this will be used everywhere in this chapter. Now here, this R is basically the radius of curvature. Basically it is this, from here till here, this is this R, okay? And okay, I messed up a bit, but I'm going to use this. This is the mass of particle. This is the velocity of particle. This is the magnetic field strength or flux density, whatever you want to call it, and this is the charge on the particle. Is it clear, everybody? Now, the last thing before we end the class, and I just want to know your input on this. Do you know what is mv in this? Do you recall a formula that's related to mass times velocity? Please don't say no. That's not fair. MV. I've
Sir, could you please show the derivation again?
yeah, why not?
why not?
So right now, which derivation? The BQ1 wali? That's
Yes,
the
sir,
one you want.
BQ.
Okay. Here it is. Interesting.
So will they ask us to draw this drawing?
The circular one,
Yeah.
they might give you a path and they might ask you to draw either the magnetic field, whether it's into the page or out of the page, or they might also ask you to draw vector of force or something like that. They can do that.
Okay.
Gatika, anything I write on these notes, it means that is important. Anything that I say is not that important, okay? But whatever is written, it means I've written it because of a purpose. That's it, okay? Otherwise, I would not do it. I would not teach you anything extra out of your scope. I'm just teaching you the things which are extremely important. That's all, okay? It means they can ask you a question from this. And as you solve the papers, you'll realize, right? You'll realize from the questions that, okay, we've done this in notes, not like that. Because it took me so many years to finalize these notes, okay? I'm still improving on them. That's how these are made, okay? Now I want to know what is MV. Who knows what is mass times velocity? Please don't say no. That's not fair.
So momentum.
Momentum.
Momentum, sir.
So it means that this is the momentum of that particle. And now we learn something very, very important, which is that the radius of the curvature depends on the momentum. So the field here, magnetic field, is going to stay constant. The charge on that particle will stay the constant. But the point is, the velocity and the mass of the particle is going to be very important. Now let me ask you one question from here, just for your knowledge. I'm not writing it. If this particle that we have shown you, that I have shown you, is the helium, which has 4 times mass of hydrogen, right? If I drew a similar diagram for hydrogen, would the radius of curvature of hydrogen be smaller or greater, depending on if in case both have the same initial speed? What do you guys say?
So, sir, can you repeat, please?
Hydrogen has, compared to helium, the mass is 4 times less, right? Hydrogen's mass. What I'm asking you,
Yes, sir.
if I basically send hydrogen instead of helium right now here in the same field with the same velocity, will it have a greater radius of curvature or smaller radius of curvature? Like the circle will be a smaller one or a bigger one than the one we've drawn?
Sir, smaller, right?
Why? Why?
So, because less mass, so less momentum.
Yes, because less mass, less momentum would mean the radius of the curvature will be smaller as well. Is it clear? Aman, Fatma, Suban, Hasanati?
Yes, sir.
So these are the type of questions you should always relate from momentum, and that will help you out. Okay. I hope everything is clear now. Please, when you come to the next class, okay, go through the notes once more, because then you will be able to understand what we're going to do ahead. This chapter is very, very long and it will take like a couple of classes to finish, okay? So I will see you on Monday then.